Hello and welcome to Science On, science communication and networking platform. You're watching live, interactive and international science stream. My name is Oliver and I'll be your host for tonight. The all-encompassing word for tonight is move, and we will see six performers in 5 performances from 5 different countries having their take on move with their own exciting experiments. So, welcome everyone, and I would like to especially welcome our audience coming to us through our partnering channels. And this is Zlepši si techniku, Brno Region, and Hiša Experimental. I would also like to thank the facility and the organization that makes these streams possible from the technological standpoint, and that is Vida Science Center. So, without further ado, let me introduce our guest performers. So, the first coming to us from the United States is Diane and Chris. Diane and Chris, can you hear us? Hello?
Yes,
hello.
We can. Hi.
Okay, great. Thank you very much. The next is Anya, connecting to us from Switzerland. Hello, Anya.
Hello, hello.
Hello. And next we have Luka from Slovenia. Hello, Luka.
Hello.
Oh, hi. Hello there. And next we have Michael from France. Michael, can you hear us?
Hello, I can hear you loud and clear.
Great. And last but not least, we have Jaffa coming to us actually from my left side.
Hey, what do you say?
Hey, hi Jaffa, thank you. Thank you for coming. And I would like to ask you, as we can hear each other, so that's audio check is done. I would like to ask you what you have prepared for us for tonight.
Well, I have something that goes with the balance and stability, but mostly revolving around revolution.
Oh, revolution.
Wheels and stuff like that.
Okay, great. Thank you very much, Jaffa. We'll see you soon. And going back to Michael. Michael, what have you prepared for us tonight?
Oh, so I'm always on the move, but it's good to stay still for a little bit to be with you. So I'm going to ask the audience to help me move things when it's my turn, and then show a couple of ways of stopping things.
That sounds interesting. Thank you very much, Michael. Okay, going back to Luka. Luka, what can we expect from you?
Well, I'll just have some fun, and hopefully you'll have fun too.
Well, that's a good expectation to have. Thank you very much. Anya, could you tell us a little bit more about your performance?
I'm definitely going to eat some salad, but I will also try to not electrocute myself.
Oh, so good luck with that. We don't want to see that. Okay, thank you. And Diane and Chris?
Today we're going to use some toys to illustrate the properties of motion.
We've both pulled together some pretty amazing toy cars, so hopefully you will join us to see those.
Well, thank you very much. Thank you, everyone. We'll see you soon. We're so excited to have you here. I'd like to go back to the audience. And I would like to remind all of you watching us, either from YouTube, from Facebook, from Twitch, it doesn't matter. We get all the comments. So please don't hesitate to move your fingers and to comment, to answer questions from the performance that we see, and also to ask questions, what you liked and what you want to hear more about, or just what you didn't get, and maybe we could take on that a little more. So that's it. I hope you will enjoy this stream, and let me officially start Science on Move. Our first performer for tonight is Luka from Slovenia. Luka, we have you there. I'd like to see you. And I would like to ask you, as an introduction, a few questions. I know that you are one of the main organizers of Znanstival. It's a street science festival organized every year in Ljubljana. Is that correct?
Yes. Well, I do help a little bit. Most of the work is on the shoulders of my colleagues, but I like to help with materials and performances.
Okay, great. And can you tell us maybe what can we expect from this year's SNANS Festival, when it is, when it is organized, and what's the most exciting thing for you that we can expect?
Well, it's organized every year in the last weekend of May. So you can check the dates, Friday, Saturday, and Sunday. It's in Ljubljana. It's in Ljubljana city center. For those of you who are from abroad, Ljubljana is the capital of Slovenia. So you are welcome to visit us. You're welcome to visit us at the last weekend of May, and you'll be able to participate in Science Festival. So SNANS Festival or Science Festival is a combination of many science shows, performances outdoors, experiments, you name it, we've got it. So best way to do it is come and see it and participate.
Great, thank you for the invitation. And right now the stage is yours, and I'm so excited to see your performance.
Well, hopefully I'll be excited to see it too. I'm watching on the screen. But basically, what can I move? I can put stuff, for example, Chris, you have met Chris. Chris gave me something that I can put on my head and I will try to move it. It's just a device with wires and 2 tennis balls. If I put it on my head, like this, it will hopefully stand on my head. But when I move, it doesn't move. So I can move, but it doesn't move. Or it can move, but it doesn't move me. So things can move me, things cannot move me. I can move things. I can perhaps move things with my hands. For example, how can I move them? I can either push them or pull them. Or pull them, like this. But how can I push them or pull them? Do I need something apart from my fingers? What can I use? I could use a stick. I could push something with a stick, or I can pull something that is attached to the stick. Can I do the same with a rope? I have no idea. Let's see. I can pull something with a rope, but I cannot push it because rope can be tense, but it breaks under pressure. Like me. So, I cannot do it with a rope. But what about with the balloon? Balloon is somewhere in between. Let's check. A bit more stiff than the rope. I could kind of pull, but if I push, it is a bit more rigid, but it still bends. Perhaps I can move something else with the balloon. Here, perhaps a little pieces of paper. Can I move them? Not too much. What about if I rub the balloon in my shirt? Ooh, much better. So I can move things without touching them. How come? What did I do with the balloon when I rubbed it into my shirt? Perhaps I put some electrons on it. Perhaps some electrons fell from it. I have no idea. Do you know? Sometimes I don't even need to rub things in order to move things. For example, I can take one piece and another piece. Do you know what this is? Sometimes I can just push things away with it. Sometimes it attracts. Is it a magnet? Or is it just me thinking how it should work? Because thoughts are really strong. Perhaps I can convince this spoon to just kind of not move on my forehead. Do I think it and it stays there because I thought it? Am I a magnet? Or is it just simply the shape of my head? I don't know. What made this spoon move? Sometimes it's enough to just let things go and they move. You don't need to propel them. Something else holds them and pulls them. It might be a magnet, it might be electricity, it might be gravity. But gravity is tricky. With gravity, sometimes, when you let go, for a brief second, it still stands still. Why? Observe carefully. So, a spring and the ball attached to it. When I let go of the string, the ball was still holding its place for a little while. Let's see it again, and you can observe it. It holds its place, and when the spring comes to it, it starts falling. So why? Why doesn't it fall when I let go? Why does it have this delay? I have no idea. Do you? Or I can use this energy of falling, energy of everything, to exhibit to you the rotational energy. The rotational energy I have in my hand, in my palm. So when I take a ball connected with a rope, like this, and I concentrate really, really hard. Look, when I put the ball right here, you see, the energy is just straight on. But when I turn my hand, you can see that I have right-sided energy. When I put it back, it stops. But when I put palming the other way, I have left-sided energy. You see, this is just me channeling the energy and then stopping it. But how does it work? Where is this energy hidden? Is it in my hand? Is it in my palm? My left palm? My right palm? I don't know. Let's observe how I can move this rope with a weight, let's call it a pendulum, in different ways. I could just simply do it slowly. If I move it slowly, the weight also moves slowly, at the same frequency as my hand. If I move it rapidly, it mostly stands still, goes up and down a little bit, but not left and right. But if I do it with something in between, you see that it starts to exhibit moving left and right. By the way, if I just let it go, this frequency is the love frequency of this pendulum. It loves it. So even if I do really, really small motions, I can propel enough energy inside for it to move. So I don't even need to move my hand really rapidly. But when I move it in a different way, I can also stop it quite quickly. How does this work? Perhaps we can take a look at two pendulums. What about if I have two pendulums of the same length? Like this. Oops. Two pendulums. So, and they start wiggling left and right. You see that they wiggle with the same frequency. Even if one wriggles really, really with a small amplitude and one with large amplitude. They have the same time in which they go from one side to the other. What would I need to change the times they need to go back and forth? Perhaps length. Let's see. You see, the longer one takes more time to go back and forth. And this is quite similar if you take a look at our legs. Our legs are also pendulums. Okay, just a bit longer and they don't have a ball at the end. Pendulums, and when we walk, they just move here and there. The longer the leg, the slower they move. So perhaps this is why little kids always run. Because they need to, because their leg is short and you see tick, 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 tick. That's why they're always running around. But you, when you are running, are you running like this or like this? Why are you running like this? Why are you bending your arms at the elbow when you are running? How fast does your hand move when you have it stretched? Or how fast can you move your hand when you bend it? Try to run a marathon or a sprint 100 meters like this and see if the time will change your best result. So, when we move, when we walk, we usually carry some equipment. And if we carry this equipment, it lengthens our arm. It's another pendulum on our pendulum. Does it bother you? Should the weight be small or large? What happens when you are carrying a large amount of weight, a large amount of groceries in the bag? Does it really change the frequency of your hand, or do you change the frequency of your walk? It's best that you find out the next time when you do that. And wouldn't it be nice when we are walking like relaxed, you know, that our legs would be kind of connected together, so that we don't even have to think how to walk. Well, we don't do it anyway, but even some kind of connection would be right, you know, some kind of cogwheels to have inside. Some animals, grasshoppers, some grasshoppers, and preferably young grasshoppers, I don't know, you have to check, they have cogwheels connecting their legs. So it would be kind of a shame when they jump that with one leg they would be a little bit slow. So one leg would already extend and then the other one, and they would jump to the left or to the right. That's why they have legs connected inside with a kind of miniature cogwheels. So when one leg starts, it propels also the other one. So only the strength can differ. But you can check this and you will see if it's only grasshoppers or also other animals. Young or old animals. I have no clue. You have to find out for yourself. And we have mentioned that sometimes with gravity, and here with gravity when you walk, you have a small problem, you know? Because when you walk, you always put yourself up and down, up and down. You lift yourself. And in order to continue walking, you have to fall down. And this depends on Earth's gravity. So the amount of time it takes for you to make the step depends on how high you have lifted yourself also. If you have lifted for 1 centimeter your hips, then they need to fall down for 1 centimeter. And you cannot pull them with your muscles, you can only extend them up with your muscles. This might not seem such a big deal, but 1 centimeter, for you to fall 1 centimeter, it's very, very small amount of time, 0.04 seconds. But in 100 steps, this will amount to 4 seconds. Is this why race walkers walk like this, you know, the strange walk, so that they don't have to lift their center of gravity up and down? I have no idea. I don't even know what I'm talking about sometimes. I don't know. But gravity is crucial, and gravity usually just puts things down. Well, it doesn't pull so much as things fall. But there are cases when things in the gravitational field go up. Do you remember any? By the way, do you hear anything? The whistling sounds. I don't. But I know that there's something behind me, in the corner. Do you know what's inside those two balloons? Can you guess? I'm using my telepathic powers and I'm kind of sensing that you are saying there's helium in one of them. Yeah, in the top one. How do you know it's helium? How do you know it's helium? Because it's up, okay? Why is it up? Because it's less dense than the air. Okay, that's a good answer. Now, the question is, how do you know it's helium? Is helium the only gas that is less dense than air? It could be hydrogen. So you don't know if it's helium or not. You don't even know where is helium, because this is a video. I can manipulate with things you see. At least one of the things I have told you today, or will be completely rubbish on purpose. How will you know which one? You'll have to make your own research. But by the way, I said things sometimes in the air can go also up. There is helium in this balloon, and helium is less dense than the air, so it goes up in the air. And here I don't know if you see it, but there's something else rising here. Let's observe what it is. It's water boiling. And boiling water, we got some steam here. Let's put it in a glass. It also goes up in the air, so we could say that it's probably less dense than the air. What about if I take another glass and put some cold water inside? And now I'll put some liquid nitrogen, really, really cold substance, in it. And let's see what happens. Will it go up or down? This one goes down. This one? First, it goes kind of down, but then it starts going up again. Now, why is that? Liquid nitrogen is really cold. Hot water, cold water. What happened? I don't know. You know, the strange thing about move is that it's also kind of obstructed sometimes by friction or by drag. Now, I'm not obstructed by friction or by drag, but I am a bit limited by the time. And the time is now over. So, I hope you enjoyed the move a little bit and will enjoy other moves even more. So, thanks.
Thank you, Luca. I think we all enjoyed at least your performance, and I would like to address one point that we promised our audience that this would be interactive, and
yes.
I know that lots of your experiments our audience could try at home, with the walking at least. But if you had any question that we could now ask the audience,
yes.
that they could answer in the comments, that would be great.
One question that I would like to ask you is, when did I really move that pendulum with my mind, with the left and right energy? And if not, do you think that it will ever be possible to move things with our minds? Just to think about something and it will move. What's your idea about it?
Okay, great. Thank you. Thank you for the question. And we can let audience answer that. And while we are waiting for answers, I would like to ask you about one of your experiments. I noticed that you had a great experiment with the string and a ball at the end. Is the ball important for the experiment, or would that work without the ball?
What do you think? It's best that you try. You can take a ball. This is, for example, a wooden ball. It's just painted red, just so that it was more visible on the white background. But do try. I'm not the one to tell you. You should really try. Try with the ball. Try with something else. I tried also with my leg. Is leg okay? Can I do experiments with leg? Can I just put, I don't know, an apple on a string? Try it. Is the pear different than apple? I don't know.
Yes, I think the people with lots of kinds of fruits will have a lot of fun with these experiments. And okay, and the other question that I would have for you, you had a lot of experiments prepared for us. And I've heard some rumors that this is your kind of a signature move to do a lot of things at the same time. So my question for you would be, how do you keep good at it when you have a lot of things doing at the same time?
How do you mean doing at the same time?
Yeah, having a lot of things on your mind at the same time and still being able to perform them, to be good at it, and that stuff.
Well, I'm not sure I'm good at it. I just like doing it.
Okay.
You know, so I enjoy doing these things, and then it's not a problem. You know, if you enjoy something, all the audience will probably know that the things that they enjoy doing, it doesn't matter how many of them you have in your mind. The more, the better.
Okay, thanks. That's great advice. And I think we're able to have a look at some answers if you have them.
Yes, this is really good. I did it with the finger. Of course, I did it with my whole hand. So at the end, I asked you, which hand do you think had the energy? This one was a distraction. At least I hope so. This one had the energy, but not the energy like, you know, the energy, the meta energy, let's say. it had the energy of just slightly moving the pendulum and giving it a little bit of energy over a longer period of time. And you see, even though I'm moving my hand really little, the pendulum started moving with a big amplitude. And if I move it in another direction, look, I can stop it in one motion. So always when you see things that perhaps you don't understand, or you do understand, look at them a bit closer or try to do them yourself. Of course, be careful that the next experiment will not be hospital. That's the only thing. But otherwise, do experiment.
Thank you. Thank you very much, Luca. It was so great to have you here. And we'll see you later. And so thank you very much.
Yeah, thank you for having me. Enjoy.
And after a great start with Luca, I would like to invite Michael on the stage. Hello, Michael. Okay, Michael, you're muted, so we'll wait for you to unmute yourself.
Okay, I said it's great to be here.
Oh, great, so we have you here. Oh, thank you very much. And it's great having you. And I would like to ask an introductory question. You were born in Canada. Now your main job is being a science teacher in Paris, France, but you are now connecting to us from sunny Florida. Is that correct?
Exactly. So just like the theme move, I'm always on the move. Yes.
Okay. And what brought you at this time of the year to Florida?
Oh, so unfortunately, I don't have a very entertaining answer to that. My mother is retired in Canada, and she spends some time in Florida. So living overseas, it's sometimes good to spend time with family. So that's a good reason to move.
Yeah, definitely. Thank you. And also, I would like to ask, I mean, I think you started, during the pandemic, you started your own science streams for teachers or for students. Is that correct? Can you tell us more? Can you tell us more about that?
Both are very correct. I could talk hours about them, but very brief mention of them. So I started virtual science camps to get kids doing experiments around the house during the pandemic. And I had such an international crowd gathering, usually from 10 to 20 different countries from each session. So it wouldn't be fair to say the pandemic's over, but once kids started going back to school in presence, I thought it was still worth continuing to bring kids together to do hands-on science. So I continue those even to this day. The next one's coming up on Thursday, if anyone wants to join, with a particle physicist from the Czech Republic as well, modeling PET scans in the home. So that's something I still do, not just during the pandemic, as well as another project for teachers, which if you want to hear more, maybe we'll leave to the questions so I don't talk my whole time just about other projects.
Yeah, that's great. Thank you very much. And also, before I invite you to take the stage, I would like to remind our audience that you can comment, you can answer the questions, you can ask questions for our performers. And it doesn't matter if you're on Twitch, on Facebook, or on YouTube, we get all the comments and we will forward them to our presenters so they can hear them, they can answer them. And don't hesitate to use your own language, even if English is not your native tongue, you're not confident in asking questions in English, you can use your own language and we will do our best to translate it. If it's language we know, we will just translate it, and if it's not, we will use Google Translate. Don't worry, we have our last resort. Okay, so with that, Michael, please, the stage is yours.
Excellent, thank you. So I really liked the experiments trying to move things with his mind. So I'm going to ask the audience to help me out and try and move one of 3 objects I found in Florida with your minds. So in the chat, please answer, and I think they're going to add the question so you can see it as well. Choose one of these 3 objects. A beach sandal, B, a seashell, and C, an incandescent light bulb. And all three of these for me just scream out Florida. Of course, the sandal and the seashell because of the beach. The light bulb, not only because the incandescent light bulb was invented in the United States, but also because when I went to change a light bulb the other day, they still use incandescent light bulbs here in Florida, even in places where they have air conditioning all the time. So any young people joining us might not know, but up until about a decade ago in most of Europe, we used light bulbs that used a tiny piece of metal we heated till nearly the temperature of the sun to make light. And there's some parts of the world where that's still the predominant lighting technology. With that introduction, let's see if we have any people who have chosen any of the objects yet. And once we get a choice, then I'm going to ask you to concentrate on the one object we've chosen and to try and get it moving back and forth with the power of your mind from wherever you're joining in the world. So let's just see, do we have any answers that have popped up yet? So while waiting for a couple of answers, just to get to this setup, you can see as I have here, it's just a simple wooden rod connecting with strings of different lengths, a long string to the sandal, a medium string to the seashell, and a short string to the light bulb. And perhaps, oh, and we see a couple of people saying A, so a lot of people like the sandal as the first one. I'll give it another 5 seconds to see if anyone prefers anything other than the sandal. Otherwise, let's give it a go with the sandal. Oh, B, just the last second. Okay, so someone prefers the seashell. Still, based on what I've heard or what I've seen, there's more people who like the sandal than the seashell. So holding these up for you guys to see, I want everyone to stare very intently at the red sandal there. I'll stare at it myself. And just with the power of your minds, we should be able to see that the sandal is now swinging back and forth. Or the seashell is staying still, and the bulb's moving a little bit, but it's not really doing that much. Now let's stop that. The second most popular was the seashell, so I want everyone to concentrate on this shell. You can see it against the background of my purple shirt, and just try and make it swing back and forth, back and forth. And we see now the seashell is moving. And of course, if you were paying attention to Luca, you'll know it's not really with your minds. I'm using science here, something he called the love frequency. And if I swing all of these at once, you'll notice, just like Luca was showing, the longer string, so the sandal, is going to swing back slower, forward, back, at its natural frequency. The seashell medium speed, forward, back, and the light bulb really quickly, forward, back. So, if I want it to appear that it's moving on its own, if I just move it at its natural frequency, if I move the rod at that frequency, for example, going to the sandal again, forward, back, and I'm exaggerating it now so the others are moving a little bit as well, but with not too much movement, we get the effect adding together each time. Same thing as if I switch to the light bulb. Now I'm going back and forth at the natural frequency, the frequency that this pendulum wants to swing. And we get the bulb swinging while the others are staying still. So that's a first set of things where you guys helped me move this with your minds. Now I'm going to look at moving and stopping. So the next experiment, like Oliver said, I live in Paris, France, so I often have a wine glass with me, to have a glass of wine, and I travel with the Eiffel Tower with me. You can see I have a miniature Eiffel Tower here, just from a key ring. And the setup for this one, I'm going to hold the wine glass in my hand, so if I let go, the wine glass will come crashing down towards the floor as the key comes towards it. But with the power of science, I'm confident that I won't break the wine glass on a hardwood floor. A tile floor, it's not hardwood. I actually don't know what this floor is made out of, but I'm not going to show it on camera, so it doesn't matter to you. So, on the count of 3, I'm going to release the Eiffel Tower and hopefully not have broken glass on the floor for the rest of the experiments. 3, 2, 1. And that was closer than I expected. We see the wine glass was safe. And so one way that you can explain this, if I can get this off of my finger, is that as it falls, 2 things are going on. Of course, the wine glass is heavier than the Eiffel Tower, so not the real Eiffel Tower, the key ring. So it accelerates this way. At the same time, it can swing like a pendulum. But if the pendulum is getting shorter, the frequency gets shorter, so the time it takes once it goes around is going to be shorter and shorter, so it'll go all the way around until it's wrapped around my finger and come to a stop. So one more time looking at that one. So there we have moving and then stopping. Going to even more stopping, I'm going to call on a friend of mine that I call John. He actually just got named the other day. Is this little toy set of bears, and the name John actually came from a misinterpretation of what I was saying it was doing. I'm just going to change the camera angle so you can see that John, with a little weight on the end, is going to be able to walk down the length of the table. So I'm going to set him in motion with this weight, bringing John to the end. So John, come on, don't be afraid. Come here a little bit. Starting him in motion. But watch out, there's the edge of the table. Stop, stop. John stopped on his own. Let's see that one more time. So, come on, John, come on, John, come on, John. Watch out, watch out, watch out, watch out. John always stops without coming off the edge of the table. Why does that happen? So, to explain why that happens, just like the wine glass falling, I have some weight at the end here. That's going to pull John down the table, and John's going to walk along as long as he's being pulled forwards. But when it gets to this point here, the string is pointed straight down. There's no longer a forwards force to keep motion going, and the downwards force even brings it to a stop. You can make your own version of this at home using any combination of something that can slide off the table and stop. So I'm going to use a special Florida combination of things here. Again, another sandal. They sell them in pairs here. I think it's because they know that people will want to do pairs of experiments with them. I can't think of any other reason why they'd sell 2 sandals at a time. And a keychain size thing of sunscreen. And so, same setup, and it's going to work just the same way. And it'll slide to the end of the table and stop. So here it's more clear to see. As it pulls forwards, come on, come on, come on, oh, stop. Then, with the downwards force, it's actually increasing the force of friction and causing it to stop. So we're going to finish up with one experiment about friction. It's one of my all-time favorite ones, and it's been a while since I had done this one. First of all, I want everyone at home to follow along with me. I want you to put your hands together. First of all, put your hands together and clap for me, because, come on, why not? But put your hands together, and I want you to start rubbing them together and see if you notice anything. And if you don't notice anything yet, try rubbing them a little bit faster. And you should notice them getting a little bit warm. And maybe push a little bit harder together. And you'll see it's making heat. So as you rub your hands together, you can create heat. So friction not only will stop things, but friction will create heat. Now, we have Diane and Chris up after me, not immediately after, I think it's like after Anya. But those of you who joined last year for Science on Join will have seen some of the things they did with friction, including boiling water, which was quite impressive. I'm going to show a similar demo, but instead of boiling water, I'm going to try and make fire using friction. So I've got a notch board where you can see, and these are from past trials. This is a bit of a finicky experiment, so I tried it like 20 times before I want to do it on camera. Each of these notches I've carved with a knife and then drilled a hole at the top so that I can spin a spindle around. As I spin the spindle, I'll be concentrating friction to a much smaller area than our hands. And by doing that, we'll be able to concentrate the heat enough that I should be able to make copious amounts of smoke. And if we're lucky, I'll get a little bit of fire. So I'm going to set this up here so that you can see the notch as I'm drilling it. I've got a power drill here. You can do this by hand, but it takes a lot more time, and I don't want to annoy you by drilling for like an hour. You've got much more interesting things to see. So this is the way of compressing the experiment to last only a minute or so. And I'm going to start drilling things. And you can see I'm starting to make smoke, but you probably find the noise a little bit annoying. So I'm going to ask for my friend Anya, who's going to join us next with her experiment. Hi, Anya. Thanks for joining us.
Happy to join.
And so as I'm drilling it, because the sound will probably be very annoying, Anya can explain a little bit why I'm drilling it and how it works. Do you think you can handle doing that favor for me, Anya?
I hope so.
Excellent. So if the sound gets annoying, I'm going to ask Oliver or Adam, who's running things, to turn down the sound on my mic or turn it off completely. And I'll just drill calmly for a minute or so while Anya explains why I'm drilling.
Wonderful soundtrack. I want to explain why Michael is actually drilling. So he wanted to show how he used to do it when he went camping back in Canada, where he used basically a handmade fire bow and spindle, but that's extremely finicky and it takes an hour, as he said before. So today he's using the spindle. As the spindle wears down into the notch board, it creates heat and really, really fine wood powder. If the notch is thin enough, the hot powder can pile up and eventually form an ember. The powder is both flammable and a good insulator, so the goal is to create a hot pile of powder to form a small ember. We can already see, as he said before, that we can see some smoke, but we're going to have to wait a bit longer. So once the ember forms, what Michael is going to try to do is to blow on that to add some air, and that air is going to help it really come to life and really make the fire going. So we can see that the smoke is really, really, really enhancing, and that is a fun part of the experiment. At one point, spindle just goes away, and now you can see that Michael is trying to get some air through that ember to really get that fire going. Let's hope we can actually make it. It looks like he's having his birthday party. But typically, when you have a birthday party, you want to take the fire out, not bring it there. But yeah, you can see that the dust is really, really small, and that you have a lot of smoke going on, and that's why Michael is trying to get to the experiment hospital that Luca mentioned before. But please don't, Michael.
Yeah. So I think my mic is on again, right?
Yes.
Okay. Thanks for jumping in with those explanations. As you guys probably saw, I kind of had a coughing fit from the smoke while trying to blow on it, and unfortunately coughed all of the embers away. So this is a failed attempt at fire by friction. I think I'm probably short enough on time. You guys don't want to see me try it for another minute or so to do it. You saw me make a lot of smoke, so from that you can at least conclude that it should be possible with all the heat concentrated in one place to make smoke to be able to make a fire that way. But as I had mentioned when I said there's a lot of different attempts that I did to make it going, if you look on the back of it, of 20 or so attempts, there's only 3 or 4 where I actually got fire going from that. So unfortunately, I'm going to need to leave this as a fail so I don't take the whole show with that. Sorry about that, but please believe me or check it out. Maybe on my YouTube channel later, you'll just see a video of this actually working, because that's the magic of video rather than live. So with that, this is one of the many things movement can do. Movement can give rise to friction, which can give rise to heat. Hope you enjoyed these experiments. Thanks for watching me.
So, thank you, Michael, very much. Don't worry about the experiment, but as shown it, I'm not sure if I saw it, so I wanted to ask you, what is the actual success rate of this, your last experiment?
Oh, so it depends if you mean once I
starting
had
a fire.
Yeah. So when I was doing it as a teenager, I was doing it with a wooden spindle and a fire bow. And there I usually got it about once every hour or 2 I spent on it. Mm-hmm. Of course, as a teacher, speeding things up with a drill. Once you have things set up right, then about every 2nd or 3rd time, you should be able to get it working well. One of the things is if you change the wood, change the drill, things like that. So maybe not the best experiment to plan right after I flew into a different country and needed to deal with a different country's power tools, different country's hardware store, things like that.
Yeah, great. Thank you very much. And already, this is the thing with experiments, right? That you experiment with it, but yeah, they sometimes fail, and it's okay. So this is the essence of science.
Well,
so
we all got to see a lot of smoke at least, right?
Yeah, and I hope you have your smoke alarms off. So
yeah. Just before starting, I pulled it off.
Yeah, great. Okay, thank you very much, Michael. It was great having you, and we'll see you later in the stream.
Sounds great. Thank you.
Okay, welcome back to Science on the Move. Thanks to everyone who participated in the previous experiments, answered the questions. It's really great. It's the essence of having an interactive stream is to have you guys answering. So on any platform, this is an interactive stream. We have all the comments. Please comment, ask questions and answer questions from our performers. It's really great to have you there interacting with the performers. And keep doing that. Thank you very much. And I mentioned and I promised you 5 performances, but we prepared a little surprise for you, a small surprise from one of our own on our Science On team and from Adam. So Adam, we have a short video from you.
This fish is quite amazing, and it's a fortune teller fish. It could tell you how you feel or what you are, if you are jealous, in love, or false, or that. Yeah. So if I put it on my hand, it moves, it curls just now. But me as a physicist, I just wonder why it moves. So we put this question to our Instagram and our Facebook, and we put question with 4 possibilities. It could move because of temperature of our hand. It could move because humanity of our hand, or if it could move because some mysterious energy just shine on it or something like that. Or it could be electrostatic from our skin, would make it move. And in the segment, we test 3 of the points of the possibilities of movement. So firstly, we test the temperature of our hand. Here is warm stove, and we can just look at the temperature of it. It is some 42 degrees Celsius, so it's quite warm but not really hot, because I can put my hand on it. And if we put our fish on the stove, nothing really happens. So the temperature, it's not the answer. Yes, so let's move on. The mysterious energy we couldn't test because we don't know the source of the energy, so we couldn't test that, but we can test the electrostatic. Here is Van de Graaff generator, and if we turn it on, the electricity it starts generating. So we put our fish on the top of the generator, of this shiny ball, and we turn it on. Yeah, it moves, but it starts to fly away. So it was different style of movement. Yeah. And the last possibility, the last reason what it could be is humidity, the moisture from our hand. So we have this piece of cloth, and we put the water on it. It's distilled water, distilled Wasser. Yeah. And if we put our fish here, yeah, now it starts moving and it curls, and this, our paper indicates, the fish indicates that the piece of cloth is in love. Yeah, so it's really cute about this piece of cloth. But what happened here? The water evaporates from the piece of cloth, the wet piece of cloth, and this water was sucked by the fish, and the fish just moved because the water makes it a little bit bigger on the one of the sides. So that's why the fish moves.
So thanks to Adam for this short intermezzo and a short break from our online streams. And if you participated on Instagram or Facebook and answered Adam's question that was there for about a week, now we know the answer was humidity. So let's get back to our online streams, and I want to invite Diane and Chris here.
Hi guys.
Hello.
And I would like to ask Diane. Diane, you are a science teacher, and I would like to ask, where did you find the inspiration to make your lectures engaging for your students?
Well, actually, my inspiration is sitting next to me. Chris was my high school science teacher, and so he taught in such an engaging way that I actually was not in his class, but a friend said, you have to come see this guy teach, and I did, and then I ended up taking the class, even though I wasn't enrolled. So Chris has been an inspiration for many years.
Mm-hmm. Thank you. And Chris, I would like to ask you, what I've liked about experiments that I've seen you doing was that you use very simple props to explain complex phenomena. And I would like to ask you, do you do your own props? Do you make your own props?
Well, sometimes, but toy stores are a big source of our equipment. Diane and I have been working together now for many years, and on occasion we make our own equipment, but quite frequently we go to stores, we go online and find things that we think will be interesting to our students and to the public.
Mm-hmm. Okay, great. So that's it from me. I'm really looking forward to seeing your experiments, and right now the stage is yours.
Thank you. Chris, hey, I got a new car.
That's new?
That's my new car.
I have one too.
Oh, wow. We call mine a buggy. What do you call yours?
A truck.
A truck. So this is my buggy. Would you like to see how the buggy works?
Of course.
Okay, so here we go. Ready? What do you think?
I think that's pretty cool, but it's pretty slow.
Pretty slow. And what would you say about how it moves? It's slow?
And a constant speed.
Constant speed. It's not. It's really kind of dull, don't you?
Very dull, actually.
Okay, well, whatever. But I've got some others. If you want to see these.
Bring it on.
Okay, I have another buggy, but this one's a little different. So maybe you'll find this one more impressive.
Okay, that's what we're talking about. We like constant speed, high constant speed.
So these both went out of constant speed.
Correct.
But what's the difference in their motions?
This one's faster.
Okay, so the red car was faster than the blue car. Okay, perfect. How about this one? It's a different. This is the first blue car. It's a different blue car.
Oh, that is different. It's going backwards.
It's going backwards.
At a constant speed.
At a constant speed. So all of these cars, actually, we used to call them constant velocity cars. So velocity is, in physics, we say velocity is speed and direction, right? So these were all constant velocity because they went at a constant speed in the same direction. Like this guy only goes backwards, and this guy only went forward fast, and this guy only went forward slow.
I've got something different, though.
Oh, really? Let's see.
Okay, check this out.
Oh, wow. You better do that again. Oh, that is different.
Yeah, it doesn't travel at a constant speed.
Right.
And so we say when something changes its speed, we say that it accelerates.
So could you show me an example of acceleration?
Well, in fact, that's accelerating, but let me show you something else.
Okay.
If I don't wind it up as much, it not only speeds up, but it slows down.
So that's two examples of acceleration.
Yes, speeding up and slowing down.
Oh, cool. So acceleration is when your velocity changes.
Exactly.
Okay, so this is called a constant velocity car. So we have a question for our audience. Is there any way that we could make this car accelerate? So we're going to give our audience a chance to do it. Now, personally, I say no, because its name is a constant velocity car.
Right.
And to accelerate means to change your velocity.
Exactly.
So
this one keeps going in the same direction.
Yes.
At the same speed. So how can you possibly have this car accelerate?
Yeah.
Oh, do we have an answer?
I see a yes. Can you suggest how? How could we change so that this constant velocity car becomes an accelerating car, if it's possible at all?
Now, Tobias says yes. You see that?
Oh, if the car is falling, that's interesting.
Exactly. Exactly. That is so great.
Wow, Lucy. How amazing is that? I wasn't expecting that.
I wasn't expecting that either.
I just spent good money for these cars, so we ain't
But we're not doing that. No.
So something else. Is there any other way that we could make the red car accelerate?
Okay, falling.
Yeah. Well, I guess.
Oh, what's that?
Hi.
Oh, that's Luke.
All right. Well, put a motor. Oh, put the motor from Chris's car into this car. Okay,
Excellent.
We could do that.
We could do that.
Let's show you an even simpler way of maybe doing this. Okay, anybody? So all I've got is a string. Is this ringing a bell to anybody? So what we're going to do is we're going to turn on the car. And I'm going to hold the string.
But it's not changing its speed.
It's not changing its speed, but what is it doing?
I guess they have to remember that velocity is both speed
and direction. So that's the key. A lot of times we forget that acceleration means to speed up, to slow down,
or change direction.
That's it. So this guy, I can make him accelerate by attaching a string, which makes him change direction. By the way, this is going in a circular path, and so we see that there needs to be a force, a push or a pull in towards the center to keep it going.
And in this case, the string is supplying that force.
I wonder what would happen if we cut the string.
Let's see.
Oh, you're prepared.
I'm prepared. Oh, look at it.
Oh, did you see it? I'm not sure the camera caught it, but it went off
On a straight line.
on a straight line. It no longer accelerated. It went at a constant velocity because it didn't have that inward pull.
By the way, what do we call an inward pull?
Well, if I may speak Latin,
Please.
it's called a centripetal force.
Which means center seeking.
Absolutely. So anytime something's going in a circle, we need that inward force.
Now, is it always provided by strings, Diane? Could it be supplied by something else?
I bet it could.
Now, I've got a bowl here and a smaller car, smaller than Diane's, and I'm going to wind it up. Oh, by the way, if I just let it go, it goes in a straight line. No surprise.
Do that over here, Chris, so
Okay.
you can see it go in a straight line.
Whoa, did you see that? Nothing is pulling inward. However, I think the bowl might provide that needed centripetal force.
How can a bowl provide force?
Well,
I
let's
think we
see.
need to
Okay.
keep it back here a little bit more. There you go, perfect. Whoa, baby!
Check that out. I got to do it again.
Do it again.
Oh, you know what? I've got two different cars. I haven't tried this one yet today. Let's see what happens. It may not work. But... Oh, yeah.
Yes. Okay, so now what was providing that inward force?
Well, we didn't have the string, but we've got a wall that pushes inward.
Okay. Okay.
And you've
cool.
seen without the bowl, the car just goes in a straight line.
Beautiful.
So that's one of the properties of matter. Things tend to go in straight lines unless acted on by an external force.
Yes. All right, well, can we do a different kind of circle?
I think we can. We have a vertical circle.
Woohoo.
Check
Yes.
this out, everyone.
Yeah.
So we've got a loop-to-loop. Now I'm going to bring back the same car that we
Can I
put
do
in the, yes, the same car we put in the bowl, and we're going to send it into this loop. Now once again, without the track, we'd be in trouble. The car would go in a straight line, but let's see what happens. Yeah.
Yes!
Let's do that again in slow motion.
Okay, it's slow motion. No, that won't work. We don't have a slow motion camera. Chris,
Okay.
But, all right,
Okay, here goes.
ready?
Yep.
Set, go.
Yeah.
Yes! Yes!
All right. So really no surprise. We've got this track that forces it to go in a circle.
But we have another question for you, I think, Adam, if you can put it up. And that is, we're going to do the ultimate ride.
The ultimate ride.
Could
I'm
you
going to
imagine?
separate the track.
Now, in the United States, we have Six Flags. That's our big amusement park thing. Disney, too, but Six Flags. And they have a lot of these looping roller coasters. Imagine they took the track apart. Can you see the gap there? Yeah. So the question is, what will happen to the car? We're going to run the car again, but now there's no track there. So
There-
we'll give you a second.
Yeah, think about that.
Well, so the track was providing that inward force.
That's correct. That's correct.
That you needed to go in a circle. And then when we did this one,
The string-
and I cut it off, it went off on a straight line.
Oh, there are the choices, Diane.
Oh, yeah. Oh.
Look at somebody says it'll complete the track. Are you
But
kidding?
how can it do that?
How could that possibly happen?
I don't know. These-
Okay, we got B, we've got
Okay.
C.
Okay. Yeah.
Let's see, B is travel in a straight line. Well,
Yeah.
that's what we've seen.
That is what we've seen.
Okay, what else? We got another C.
Yeah. All right. Well, I think.
We better try it.
Yeah.
Now, this is nerve-wracking, folks. I want to
Yeah.
tell you, because I love this car, and I don't want anything to happen to it. Cost, okay,
It's hard to.
very expensive, hard to replace.
Okay. Are you ready, sir?
I don't know. My hands are sweaty. All right. Wait a minute. Oh gosh.
All right. Are you ready?
No, not really, but do it. Do it.
Wait. Ignore that.
Yeah.
Ignore that. Okay, here we go. Are you ready now?
Yeah.
Here, I think if you... Okay, ready?
Yeah. Did it do it or did
Well,
it fall?
sort of. I think you kind of knocked it at the end.
I know.
In your celebration. All right, one more time.
By the way, they're going to take us off the air soon, but we'll be here doing this all day until we get it right.
It's like 1 o'clock in the afternoon here, so we've
got
got
all the time in the world.
All right,
Okay.
ready?
Yeah.
Set?
Yeah.
Go.
Oh, shoot, once more. Oh, this has got to work.
Oh.
As they say, teachers always say, this worked before class.
Put this one down a little bit more. and that
Okay,
one up a
okay,
little bit more.
okay.
Ready?
Yeah.
Set, go.
Woo! 75.
All right, woohoo!
All right, so,
Thank goodness.
so at the very top, the track was missing. And the question is, who supplied the centripetal force? Well, there is an agent at the top that we don't see. And that agent is?
Gravity.
So at the very top, gravity pulls straight down, and it's just what we needed for the car to complete the track.
Do you have any other cool circular motion toys?
You know what? I have to show them this.
All right.
This is the cutest thing. Okay, now I don't want it. Okay, I don't want it to take off, because it's wild. Whoa! This guy's wild. Okay, can they see it? Oh!
Yeah, I think they can.
All right. And I've got a little sphere, clear sphere. I'm going to put the car inside. Oh, it's excited.
Oh.
All right, whoa.
Let me turn down the lights.
Look at that.
Woo, baby!
Look, that car is orbiting inside this little plastic sphere. And if I were to open it up, it wouldn't be pretty because the centripetal force would be absent and the little car would go into the kitchen.
Yeah.
It would fly away.
Yep.
So notice that it moves beautifully both horizontally and vertically. So this is just one more example of centripetal force changing the motion of an object that wants to go in a straight line.
Now, today we've been using a lot of toy cars because, well, they're just cool, right? So I wanted to show you my new car. So this car is really cool. Let me turn him on here. So this little red car, he's cool, but he comes with a laser, and he follows the laser where you tell it to go. Isn't that cool? But it's even better. Hold on, I gotta move the camera now. It's even better. Go like that.
There you go.
There we go. Pretty good. All right, here we go. Can you see him? He's on the wall. Isn't that just amazing? And you may ask, how does that work? And what we say is, we'll leave that to another time.
Thank you very much. We've had a blast.
Yeah, I hope you enjoyed it. Take care, everybody.
So thank you for the show. It was such a great show. And I can tell you that everyone who was seated here in the studio was right at the edge of the seat when you were trying the loop experiment. And yeah, we just burst out when it actually happened. So yeah, it was great. And even though it was about physics and Chris's t-shirt actually says physics, I think it was some kind of chemistry that worked here that made this a great show. So thank you for that. And also, I would like to ask, you mentioned these theme parks and amusement parks. So do you still go there? And if yes, or if you did or used to, what is your favorite ride? Maybe even from the physics perspective.
Ooh.
Well, yeah, you do.
Oh, okay. One that made me ill, but I really enjoyed was the rotor. And that's the cylinder where you are pinned against the wall.
And then the floor
drops.
Yeah.
And friction keeps you suspended above the floor. Mm-hmm. But I can only do that once every 5 years because it makes me so sick.
Yeah. Yeah. I think I've always been a roller coaster fan, but I don't like the drops. So I really liked, we used to have a roller coaster here that started out on ground and it accelerated and then it went through the whole thing. Instead of using potential energy, it used mechanical energy or kinetic energy, I should say.
Yeah, I'm a coaster guy too, I have to admit. Yeah.
Okay. Okay, thank you. Thank you again for the great show. And Chris, as I mentioned that I love that you use props. I came prepared. I knew that you were going to use cars, so I came prepared with my t-shirt. So yeah, I have that. I was prepared for you. Thank you again, and I'll see you soon at the end of the stream. Thank you again.
Take care.
Welcome back to Science on Move. Thank you again for everyone who participated in online comments and answering the questions. It's really important for us and for every performer that they get feedback from you. And don't hesitate to ask questions. We will have a session at the end of the stream where we will ask your questions we'll forward your questions to our performers, so we'll have an ending discussion there. So don't hesitate to ask the questions or in English or in your language, it doesn't matter. And you can use Twitch, YouTube, or Facebook for that. And so let me introduce Jaffa to our stream. Welcome, Jaffa.
Oh, hello again, or perhaps with this awesome stuffed weapon, should I say Jaffa Cree? Perhaps, I don't know.
And Jaffa, I know that you just recently successfully defended your PhD thesis. Congratulations to that.
Yeah, thanks a lot.
And what are your plans for the nearest future?
Well, I don't know actually. I've been doing a lot of stuff recently. I've been doing these activities in Vida Science Center. I've been preparing some teaching materials for school kids. And I have a lot of concerts upcoming and recent, so we'll see where it goes afterwards. But now I'm in this intermission stage, let's say.
Okay, great. And I would also like to ask about some other rumors that I heard. And I've heard that you like to take an experiment, then turn it upside down, then completely around, and have something completely different from what it was in the first place, but much better. Do you have any recent examples of that?
Well, I don't know if it counts as a successful example, but let's say I was trying to make Rupert drops, Prince Rupert drops. It's a famous experiment with melting glass and making some glass droplet which is under high stress, which makes it incredibly resistant to, let's say, blows. But as soon as you break the tip, it will explode or implode, let's say. But I didn't manage to do it until now. But when doing so, I just figured that even when you cool down molten glass, it just cracks so beautifully that maybe this is a thing on its own. Okay. We'll see.
Thank you very much, and thanks for not destroying it and not bursting it to our place.
Oh yeah, and there are probably some fire alarms, so I won't show it now.
Okay, great. Thank you for that. So yeah, without further ado, the stage is yours. So please show us your experiments.
Thank you. So, did you ever give a second thought to the physics that's behind riding a bike? Because I know it's such a common skill. Everybody does it, and maybe everybody learns it by trial and error, by experience, intuitively, which perhaps does the best job in the end, but doesn't let us learn all the tricks that are behind the riding bike. So, I have this little tiny bike model with this adorable reindeer, and let me start with giving you some question. What do you think a bike, not this bike in particular, but any bike in general, for any bike, what is the distribution of weight between front and rear wheel when it's standing still on a horizontal platform? What is the distribution of weight? Is it A, 50-50? B, is it dependent on where the center of mass is horizontally? Oh, sorry, vertically, that's B. 3, C. Does it depend where the center of mass is horizontally? And D, it will be always more inclined or more mass resting on the front wheel. Not, I remind you, not this bike in particular, but any bike. And before you give me the answers, I'd like to invite you into a short experiment that you can actually play along with me. It's a bit hard to tell by now, but as soon as you'll get the screen, you will see what I mean. It's a ridiculous simple experiment where you can, where you only need something that's straight and, let's say, smooth. And perhaps this experiment will give you a clue, but please try to answer during the experiment, not afterwards, so we can go straight to the answer when we are finished with the experiment. But feel free to join me. So I have a long rod, be it a ruler, pencil, rod, walking cane, whatever. And I'll place my hands at the opposite ends. Now I will start sliding my hands towards each other. And as you can see, they met in the center. And as it happens, this is the center of mass of this tube. Well, that might be a coincidence, just because I started with my hands stretched evenly and because I was going so slow. Let's try to do something different. Let's try to go at higher speed. Still almost the same. Okay, let's try to twist it a bit more. Let's start unevenly, yeah. Again. And finally, you might accuse me that I was not trying enough with this hand. So I'll try to actively move this hand, which is closer to the center, to get a different result. Let's go. Didn't work out. It always ends like this. And the reason is that we are experiencing different pressure on each hand. And the pressure is greater whenever you are closer than to the center than the other hand. So this hand will experience more weight than this one. And more weight means greater pressure. Greater pressure means greater friction, worse movement, worse sliding. Therefore, worse sliding, this hand slides better. Until about now. Now there is more pressure. And we're there, always in the center. So now you probably could decipher what was the first question about. And if I could see the answers, perhaps. So A, 50-50. B, depends on the vertical. C, depends on horizontal. D, always on the front, there's more weight. So how did we fare? We got some C from Tobias, B from Sarah, C, B from Paul, and C from Lucy. Awesome. Looks like C. Well, you might be right, it actually is C. It doesn't look like, but is C. And there's, however, something I didn't tell you, you might say. We explained what happens, that there is some pressure, but you know, there is always a rabbit hole when you are speaking about some physics problem. You can explain one thing, and another question about the explanation arises. So the next question is, how is it possible that there is bigger pressure here, that there is more weight here? I just described what happens. I didn't explain the next step. So this I would like to introduce, for this I would like to introduce you to my helper, white box. Yeah. Some of you might probably heard about the first Newton law, law of inertia. If there are forces acting on a body that cancel each other, you can sum them, one goes there, one goes in the opposite direction. Let's say like this. Oh, then there is no translational movement. Translational movement goes like this. No translational movement if I apply these forces so that they sum up to 0. let's try. 1, 2. Same forces, no translational movement. But there's another type of movement which I could achieve with just these two forces. The same two forces, and I apply it. And you can see the center of mass didn't move anywhere, but it started rotating. Completely different kind of motion. And so you might think, if there is a law for inertia, for the translational movement, there might be another law for rotations, and you'd be right. Only instead of sum of forces equals 0, you get the sum of force moments, or torques, as we would say, must equal 0. For that, I would like to probably show you my drawing skills. So let's try. We have a let's say some seesaw that has a rotating axis like this. Imagine there are children sitting, yeah, and you are trying to move them up and down, and so on and so on. So let's imagine a few forces that would act on this. How do they make these moments or these torques? Well, torque is simply force times the distance, but it's the perpendicular distance. What does it mean? It's the distance of the line of the force from the axis. I think, however, it would be much more charming to evaluate these moments by simply drawing these shapes. Each moment is then equal to the area of these tetrahedrons, parallel tetrahedrons. So you can visualize actually the action of moments. This one obviously turns in this direction. By simply adding up the force, you have 1 point, 2 points, two points of the force and the axis. You make the third point and then continue drawing. The size of this tetrahedron is exactly the magnitude of the moment. Yeah. So what does it happen with force number 2? It's much smaller. Obviously, it turns into the other direction as the axis is here. What about the force 3, which seems reasonable enough, but unfortunately, this force does very, very little. And force number 4, which goes straight through the axis, does nothing at all. Now, let's try to look on the rod that we made before. So we have a rod. There is some gravitational force, and I was holding one hand over here. Let's say over here. So there is my axis, and the gravitational force has, let's say we have 2 to 3 distances. Yeah, the whole length is 5, so it's 2 to 3. So this moment is 2 times g. G is the gravitational force. So how much does need the other hand, let's say it's violet, push here so that it wouldn't rotate, so that the sum of the moments would be 0? Well, simply this much. We only need to equate the sizes of these two rectangles. So it's 2 times g equals 5 times something. Obviously, the something will be 2/5 of g. And now we see that on this end, when there's 3 to 2, we get 2 portions of the mass here, and the 3 portions will be here, which we would get if we were to try with this axis of rotation on the other end. So, long story short, the moments distribute in the opposite ratio to the ratio of the distances, the perpendicular distances. And where does the bike go? Well, again, if there are two wheels and the center of mass is here, then obviously more weight will be up here. Well, that's for now enough of drawing, and let's go to the wheels. So, and to my right. So this bike is quite symmetrical. So I'd say it's about 50-50 for now. But perhaps if you would put it on a slope, do you think it would change? It's a short question. You don't have to answer by default, but if you feel like writing something, feel free to do so. So if I have a stopped bike in here, what do you think is the distribution of weight? Wow. I wouldn't ask so stupidly if it was clear. It's not. It's always tilted more to the side downhill. And why is that? Well, let's go back to the drawing for a while, only for a while. Even if I had a bike that has the center of mass around here, then it's obvious. This is much closer to the point on the front wheel, which is the axis of rotation, potential axis of rotation, than to the rear wheel contact point. But even if you were to have completely symmetrical bike with the center of mass in its middle, it still would tilt to the forward, just because the contact point is not under the center of the wheel. It's a bit backwards. So at all times, unless your center of mass is on the ground, at all times you'll get more weight on a downhill wheel than on the uphill wheel, than it is in the situation where we are set horizontally. So I think we have enough information for now to resolve the moments of a bike that is rolling downhill and maybe will be braking. For that, only one more apparatus is needed. A slope. Well, so if I was to let go of the bike downhill on these belts, it will slow it down. What would happen if it was slowing down on the front? You have to see that this front will adhere to these belts, well, the back one. So there will probably be some difference, or will. What do you think? So, I'm sorry, I need to decouple my... And I managed to squeeze off my microphone. I'm so sorry. hopefully we'll be all right. So, as you might have seen, there are accidents on a bike if you are braking downhill, and we'll get to the bottom of it. So, let's try to go with the front brake. Yeah, so the front wheel will be sticking, and let's just give it a small try, like this. Yeah. So it might just fall down. Something that happened to me about 26 years ago when I was going downhill, and I marvelously flipped over my wheel and went to sew my head to hospital for adults, which was awesome for me. But my question is, if it actually falls, what is the cause for the fall? What is the cause for the reindeer to break his head? So, is it A, because it's the center of mass of the bike will shift forwards? B, during the braking. B, will the center of mass shift backwards during braking, which will cause the reindeer to fall over? C, the braking creates additional lasting force resulting in additional torque, making the leap. D, the braking creates additional momentary force, a short time pulse of force that that helps or that will make the leap. So let's give it a try before you write your answer. So I'll just remind the answers. A, it's because the center of mass shifts forwards of the bike. B, it shifts backwards. C, there is a lasting force that makes additional torque. Or D, there is a short momentary force that will affect the braking. Okay, so let's give it a try. I'm a bit worried. Sorry. So 3, 2, 1. Oh! Yeah, lost his head. Now let's take a look on your answers. So there were B, the center of mass shifts backwards. Any other answers so far? No. Okay. Well, the thing is that the bike stays as it is. It's just bike. There are no moving parts, so there won't be any redistribution of the mass, and the center of mass will not shift with reference to the bike. But when we arrive here, the surface adds an additional force that acts in this direction on the bike. And if we consider this axis of rotation, this force will make the bike turn like this. And it's lasting because it's now and now and now and now and now and now. It's almost the same all the time. There would be a different kind. So, in short, C is correct. If I was to go backwards, let's say I was braking with the rear wheel, that would be something different. Let's say we try it now. Sorry, reindeer. 3, 2, 1. Yeah. So the problem is that the torque initiated by the rear wheel is the same. It actually flips the bike over, but by flipping over, this wheel lightens up, meaning this force vanishes. It's only momentary. Which is also why brakes on the back wheel are less efficient for you, and you cannot really rely on them. But you have to be very cautious about your front brakes. So that's all for me. As a small bonus, you might want to see the inverse effect, which would be full throttle uphill. So let's try that. And just let me make a reference to my experiment. It's not exactly 100% real situation because our bike is a bit different from the real. We do not choke the wheel here, we choke it from the down, but it's close enough. So let's try the full throttle. 3, 2, 1. Bye.
Okay, thank you very much, Stefan. I mean, I don't know if this reindeer got enough appreciation from you. I mean, you knew that it would crash, but you chose a Christmas reindeer. So what was your reasoning behind that?
Huh? Sorry.
What was your reasoning behind choosing a Christmas reindeer for your fall experiments?
I don't know. I have nothing against Christmas. I like getting presents. So if you want to send me some presents, I'll give you my account number. Don't worry.
Okay, thank you very much, Jaffa. I mean, I love your props. They look, yeah, they look good. Let's say it like that. And I'll give your reindeer back to you. And thank you again. I hope to see you soon at the end of the stream and for the ending discussion. And we'll go further with the stream. Welcome back to Science on Move. You're watching a live, interactive and international science stream. I'm so glad that you still answer to our questions, you still interact with the comment section, and please do that until the end. We'll have the discussion at the end, and we will forward your questions to our presenters, to our guest presenters, and we will get to them. And the last presentation, and we're so excited for it, will be given by Anya.
Hello.
Anya, welcome back.
Thank you. Good to be back.
And Anya, when someone wants to reach you out and wants to see you in your natural environment, by that I mean working, they would have to visit CERN. I mean, that's CERN, that particle accelerator CERN, right?
More or less. You can see me in my natural environment also when I go back to Slovenia to perform science shows in Znanstival. But yeah, more or less, CERN is the best bet.
And can you tell us more about what are your responsibilities at CERN?
My main responsibility is to play and have fun, but other people might recognize that as creating and performing science shows. So, as we all know, that's really just about playing and having fun.
Yeah, this sounds like a dream job.
Oh, yes.
For me. Okay, great. Thank you very much. So, no more questions to you. So, let's do it. The stage is yours.
Okay, thank you very much. As I promised in the beginning, I'm going to eat some salad. But this is not really the experiment that I want to talk to you about. Although it's quite delicious. I must say, very good midnight snack. What I want to talk to you about today is moving, just movement. And you've seen a lot of experiments. Some of them I want to repeat. The first one is the one that Luca did before. I won't take long with doing it. It's just, he took a balloon, he rubbed it into something. So let me rub this one in my lovely shirt. And what we know is that if I take a bowl of fake salad, it's not really salad, it's those things that you get in a package if you order something home. If I put the balloon closer, what we get is some of these fake salads flying out. So as Luca before mentioned already, this is because we have transferred some charges here from my shirt. So we currently don't really know, and we're not really going to go into that. What we do know is that this balloon got charged, and because it is charged, it attracted some of these things in the salad bowl. And because these things got attracted, they started moving around. So we can use charges or charged things to either move something else or get moved themselves as well. So this was for the first thing. And one example of this, of charged things moving, especially electrons moving, we can also see in nature. You've probably already seen a lightning bolt. So you could see lightning outside going from the cloud to the ground. And this is really because the clouds are basically they are like very charged and very big balloons. So a lot of charge gets gathered on those clouds, and then when there's too much charge, the charge gets, I don't know, it just doesn't want to be there anymore, so the charge will get transferred from the cloud into the ground, and then we see the lightning strike. But I'm wondering, how well do you actually observe lightning? Or how well you observe anything around you? I'm pretty sure you've seen it before, but do you know what color lightning actually is? So put your answers in the comments and we'll talk about them a bit later. But first, let's talk about whether or not we can make lightning here. I wouldn't be bringing another experiment on the screen if I wouldn't be able to make some lightning. So what I'm going to do here, I'm going to try to mimic how lightning in the sky, outside, also happens. Basically, what we would have is we would have a very charged cloud and the ground that is either not so charged or would have opposite charge. So here we want to make one of these balls, if you can see it, so one of these balls is going to be a cloud and the other one is going to be the ground. So it's going to be a mini lightning. And I'm going to repeat, well, almost repeat another experiment. And this experiment was done by Michael. Michael actually noticed that if you're doing some friction, so like rubbing your hands or if you're drilling into something, what you're creating is basically heat. You can create heat, you can stop motion, but another thing that we can do is also transfer charge. That's why charge got transferred between the shirt and the balloon before. And if we do that very much, so very quickly and quite a lot, we can get a lot more charge. So what we're going to do here, here we have tiny brushes that they're touching upon these two circles. And I will start moving these circles around, so they're going to be brushing against each other quite a lot, and we're going to be able to get some charge out of that. Okay, so now I see that we already have some answers. One said blue, white. We have another one that says purple, and another one that says blue in the air. That's a very specific answer. And let's see exactly what we can observe in this experiment. So I'm going to start rolling this around. We're going to start brushing these brushes against the circle. Oh, have you seen it? Huh? Exactly. So we have here bluish, blue-white kind of lightning. And exactly as Pavel just wrote in the comments, the color of lightning actually depends on where the lightning is happening. So this was just one example of lightning, and we're going to use this device in a couple of seconds again. I just want to show you that really the color can depend. Because if I take this tiny thing, this is a plasma ball, and what we get here is, again, we put a lot of charge in the center and we want to, well, the charge wants to get out. And if we turn this on, if I found it, good, we can see quite a different color. There's some blue, very strong blue in the center, and then we have some pink in the end. So we can see that lightning can also be of a different color. Why is it a different color here than it was in the previous experiment? Well, the previous experiment, the lightning went through air, just as Lucie wrote before. And if we look at it in this ball, here inside we don't have regular air, we have some specific gas that will make this be in a different color. But this was just a fun fact. Let's go back to moving. So in moving, what we do is we have a charge in one space. In moving with charge, what we do is we have charge in one space and then the charge gets someplace else. This is a principle that we are using at CERN all the time. So CERN is the biggest particle physics laboratory in the world. And what we're doing here is we're taking a charged particle and we're accelerating it so much that it reaches almost the speed of light. So it's really, really, really fast. If you want to know how fast that is, at the end, when it gets to, well, basically just 3 meters per second less than the speed of light, that particle has the energy of a flying mosquito. Well, I know that's not really that impressive. A flying mosquito typically doesn't have a lot of energy, but if you put all of that energy in a tiny, 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 tiny particle, then this energy actually means quite a lot. But let's see actually how we get these particles to accelerate so fast. So we're going to use this device again. This device, just so you know, is called a Wimshurst machine. So we're going to use this device to accelerate not really a particle, but let's accelerate a ball. So what I have here, if you can turn on the second camera, is a very, very long, well, not a very long, but a long rail. And this rail has some copper strips here and there. And these copper strips are going to be connected to my Wimshurst machine. So one side is going to be connected to one side of the machine, and the other side is going to be connected to the other side. This will technically mean that each of these lines is going to have the opposite charge. So one is going to be negative, the next one is going to be positive. Then we're going to have one negative and one positive and one negative and one positive, etc., etc., etc. Okay, then what is going to happen? We're going to have this tiny ball. This is the camera. So this ball is colored with a specific color, and this specific color is actually a conductive paint. Because of this color, this ball actually gets charged the same way as the strip on which is on. So if this strip gets charged negatively, the ball is going to get negatively charged as well. And negatively charged ball doesn't really want to stay in a negatively charged place. So it's going to want to go to the positive charge. So for example, if this is the negative, it's going to want to go to the positive. And then it's going to get charged positively again. And let's see exactly how this rolls out in an experiment. Okay, I'm going to start by turning the Wimshurst machine again. This time without any sparks, hopefully. And let's see what's going to happen with the ball. The ball got stuck. Let's see what happens with the ball if I just slightly move it. Yeah. Can you see it? It's going, it's going, it's going, it's going, it's going. And it's going to go in the other direction again. And it's going in the other direction. And I can continue doing that as much as I can. But at one point, this experiment just stops being so interesting. But what you can see is really the ball got accelerated because of the charges on the different spots. In order for me not to get electrocuted, I will discharge this whole thing, and you will see as soon as I stopped this, as soon as I discharged this machine, the ball stopped. So we need this electricity, we need this electric field in order to get the ball moving, and the same thing we need if we want to get a particle moving. So if we want to get a proton moving, we need an electrical field. But the thing is, if we want to get a particle moving very, very, very fast, at some point we run out of space, because we would need a very long strip like this for the particle to go faster and faster and faster to be accelerated more and more. And then we don't even know where we would fit that. So they kind of came up with a very good idea. What if we would do the same experiment, but in a circle? And this is where my salad bowl comes along. So let me just unhook this thing. We're gonna take our proton, move this linear thing away, and bring closer the salad bowl. So this salad bowl is made in a very similar way. We have these copper strips, and these copper strips, basically, we charge one positively and one negatively, and then because these two meet in the middle, this one again is going to be positive, and these here, you can see on the side, they're also connected, so these will all get negative. So positive, negative, positive, negative, positive, negative, positive, negative. And it's going to go around and around and around. And let's see if we can get this ball moving in a circle as well. Okay, I hope you're ready. Let's go. 3, 2, 1. Starts. Let's see. If we move this like this, it's going to be better. Go to the strip. Yeah. Now we have it. More charge, more charge, more charge. So this salad bowl accelerator also shows us a very the principle that Chris and Diane showed before. So if we have something circular pushing the thing inside, what we get is the ball starts moving in a circular motion. So again, we're talking about the centripetal force that they mentioned, and we have the ball in a nice circle. And with this electrifying experiment, I will now finish my show. I'll try to be on time for once. Typically I'm not, but I'm from Switzerland. I'm supposed to be. So let's try this one. I hope you enjoyed it, and I hope you have some questions I can answer. Maybe not all of them. We'll see.
Thank you, Anya, for a great presentation. It was, actually the first time I saw a ball accelerator, and it was eye-opening for me that how you can accelerate. And actually, we have a question from audience, so from YouTube. And Olaf asks, and so are the copper stripes all at the same distance? So it was not easy to see from this perspective. I think the question actually refers to the linear motor.
Yes, linear one,
so
of course.
Can you comment on that?
That is a fantastic question. I really hope that someone would ask that. So yes, these copper lines, especially if you can turn it to the camera, the other camera again, I can show you the beginning. So in the beginning, we have quite some difference. So the beginning ones would be closer together, and then the further they would, the ball would go, the further away the lines would be. Why is that? That is because here we're really talking about what Chris and Diana were talking about before, and that's accelerated motion. So at every time it moves, it gets accelerated slightly more. So in the time it needs to get from one to another, in each interval, it can go a bit further. That's why we get increasing lengths. The only thing is, why did I want to turn it around to show you this, is that this ball that we're using is not ideal. So in the end here, we still need to go to equal distances, but that's because of friction, because of air friction. So all of this kind of in the end doesn't really show the real picture. But in the beginning, we of course need to have the lines closer together to even get the ball moving.
Mm-hmm. Yeah, that's very interesting, Anya. Thank you for commenting on that. And I guess we will have more questions later. And Olaf also appreciates your answer. And we'll have more questions for the final discussion later. So thank you for now, and see you soon.
Thank you.
And as I said, Anya concluded our block of performances, and we will go to discussion session that we have at the finishing line of our stream. And again, I would encourage you all to comment, to post your questions. You can ask anything. You can ask about their hair, you can ask about their outfit, you can ask about their experiments, you can ask why they work, where they work, or anything else. And with that, I would like to invite all of our guest performers here online, and also Jaffa, that is right next to me, for the final discussion. So I see Chris and Diana, I see Michael, I see Luca, and I see Anya. So, okay, great. Thank you for joining in. Thank you for following us for the whole time. And I would like to ask Luca, because we haven't heard from you for a really long time, and we actually miss you and we miss your voice. So Luca, did something particular during the stream excite you or make you wonder about something that you would want to pinpoint and ask other performers about?
I like that. You know, I think we were all a bit on edge watching the cars go through the loop. So, as you mentioned already, I liked bits of all presentations. You know, because that's at the end why we stayed and watched, because we like to steal ideas from each other. So basically, that's it. I liked the way. I like the way I've never seen the way Anya showed the circular accelerator. I've seen only linear ones, so this was a nice thing that I will probably steal. And plenty of it. I don't know, a question. If you want me to ask a question.
Yeah, if you have one, if you don't, you may ask it later. No problems.
I have no plenty of questions.
So just choose one.
What are Chris and Diane? One question that perhaps is on everyone's mind. What's the name of the dog?
Yes, for Chris and Diane. Yeah, Chris and Diane, we can't hear you. You're muted.
Sorry, that's Cooper. That's Cooper. He's a golden doodle.
Sheldon?
No.
No, Sheldon, that's Cooper. Okay. Thank you, Luca.
Have you ever tried, Chris, putting two cars together in the bowl?
Oh, no. Gosh, we got to do that.
Well,
Hey.
Yeah.
We just happen to have.
Whoa!
I'm not sure we're coordinated enough for this.
Luca, we'll have to work on this next time.
You bring it. I have two waiting for you for Science-Tival, so you can try them.
Mm-hmm.
Wonderful.
Wonderful. And Chris and Dan, while we have you on the main focus, so do you have any comments to your fellow presenters?
Like Luca said, we learned a lot today, and we will steal your ideas, by the way.
Yeah. It's so nice to just see other science communicators from all around the world. And it's just the joy and love of science and exploration is what really joins us all together. So it's
it was great sharing with all of you today. Thank you.
Thank you very much. Yeah. And may I ask also, Michael, did you were you able to follow all of your fellow presenters, and do you have any questions on them?
Yeah, of course. And I love them all. So I've got more questions than you could possibly want to give me time to ask. There's two that I definitely want to get a chance to ask. But before I ask any questions, I also want to say I really loved Jaffa's experiments on the bike. You'll see I'm wearing a bike t-shirt. And just by curiosity, any participants in the chat, mention what country you're joining from if you think I might not have biked across your country. And I'll see, I think there's only Dave Fish, if he's still on there. That might be the only one who I haven't biked across your country. So I know a lot about bikes. And when I first saw Jeff's experiments, I thought, well, what about when you're on a hill? What about when you're on braking? And then he covered it. So like I was setting myself up to be disappointed for something I expected someone to forget. And then it was just beautiful how you covered all of the questions I had. So no questions there, just awesome job. And then one that's kind of a compliment mixed with a question, both from Luca and Anya. I've been inspired to go to Zanzibar. So a question for everyone. Who all from us here is going there? And I kind of follow up to that question. I know there's at least one teacher who's watching, NASCO in Bulgaria, who's interested in information on it. Can someone who has information to send either like jump on and say that or add like links for him and anyone else trying to go there? And then if I'm allowed to ask another question after someone jumps on to answer that.
I'll just write it down and I'll show it on the camera because I kind of don't know how to. I can only chat in private, so I'll just write.
Yeah, look at it. That's the improvisation that you're really good at. So yeah, you really shine with that. And yeah, so we can wait a little.
Okay, so the program is still not on because we are finalizing it. But the dates are already, and you can see the gallery of the previous Znanstevals. The program will be on probably in the second week of May. Might be sooner, so check frequently.
Mm-hmm. Yeah. So just to read that, it's www.znansteval.si. Mm-hmm.
And a pro tip that's been passed on to me from Anya about getting there is often Ljubljana is a surprisingly expensive city to fly into. So there's a number of airports that are a not unreasonable bus ride away, like Trieste and Zagreb and a handful of others. So take advantage of that if you're put off by the price of flying to Ljubljana for it.
You discovered that, didn't you?
And then, am I allowed to ask one more short question, or is that my question's done?
Yeah, sure. Go ahead.
Okay, so a question for Anya. I love that you referenced my experiments for the heat, explaining the Wimshurst experiment. And this is something I've often discussed at length with a number of educators. Is heat required for a transfer of charge? And can you prove or disprove that?
I can definitely not prove it, because that's not how science works. But that is a very, very good question that I do not have an answer to.
Okay. And can I offer to show a simple experiment to show that you can transfer charge without heat?
Yeah, go ahead.
Perfect. So I'm just going to show my table here and some regular Scotch tape and put 2 strips of it down. And some of you may be familiar with this one already. But without rubbing to create any heat, just contact and lack of contact, which can happen when you're rubbing things to transfer charge. If I pull these apart quickly, I'll transfer charge to each of them. And we should be able to see they're repelling each other as I try and bring them near. It's pretty weak, and I'm in a very humid environment, so the charge is going to be lost. but hopefully that shows that they're being repelled. So they both receive the same charge. So like it is possible to demonstrate that heat's not required, although in a lot of situations, like in a LINAC, you have a hot filament because the energy required to remove electrons is less. But for like simple rubbing, usually the heat is just a coincidence that you're getting at the same time.
Yeah, but sorry, just one question. I like to question.
I love getting questioned and contradicted because that's how I learn too.
Yeah,
so
when
please
you
tell me I'm wrong and explain how.
When you peel it quickly off, you will always generate some form of heat. So is it really a proof?
So I'd say from that point of view, no, it's not a firm proof at all. Yeah, but it helps show that friction itself, or like the idea of movement to generate heat, isn't necessary.
Yeah. By the way, do you probably know it, but you only showed the first part where you glue two of them like this. Do you know what happens if you glue one on top of the other?
So like this. It's prepared at the side, but I figured I didn't have time to show.
Yeah, could be. Do it.
Well, okay. So here's two that were together, and then they'll, if I don't make a big mess, they'll be attracted to each other. But if I remember which one was the top one and which one was the bottom one, I think it's the top one in this hand. So I'm going to pull them apart. And the top one and top one should repel. With the breeze, it's hard to get anything conclusive, but the top and the bottom should attract. Very inconclusive with the breeze I'm dealing with here. But like, was that what you were leading to with that?
Yeah. Just show it.
Great demonstration with what you have. That's great. Thank you, Michael. And also, I would like to ask Jaffa, as you're here, were you able to follow the other presentations?
Well, a tiny bit, because I was kind of in the process of preparation, and we were here sort of in silence, and there were not enough headphones or earphones. So I was following some of them mute, which was kind of funny, because I was so expecting what the experiment will turn out to be. So somebody was already all informed, and I was watching. Oh yes, he means the pendulum. Yeah, well done.
Okay, great. I mean, the experiments from Dan and Chris could translate very well even without sound.
Yeah.
So that was great. And I believe we have some questions from the audience. If we have them, can we have them on the screen, please? Yeah, from Astro Alpha 91 from YouTube. But aren't you rubbing when you're fixing it? I'm not sure who to ask the question. Maybe
for Michael. Yes.
I think for me, like if the act of like putting tape onto a surface involves rubbing, I'd say it could, but like it doesn't necessarily, or like by the nature of sticking when you stick it, then it doesn't need any translational rubbing. It's just like an on or off. So like perpendicular to the plane that's stuck rather than parallel to the plane of the surfaces. So like from that point of view, I would call that not rubbing, but I mean, it's maybe a question of vocabulary or semantics at that point.
Yeah. Okay, I understand that. And if we have another question from the audience, we can show it now. But I have some prepared. Oh yeah, from YouTube as well. So awesome sounds.
Well, that was actually me writing on YouTube. That's from my YouTube channel.
Yeah. Okay.
And that was for experiment, right?
Yeah, that was for Anya, right?
And it was at the moment that you had the Wimhurst, and I was just amazed at how cool the sound from the Wimhurst was. So I was wondering if you had like a special additional mic, or like if you practiced that sound, or yeah.
No, it just makes really this amazing sound when you start turning. It really makes a crackling noise. It's really fantastic. I don't know how it sounded like via microphone because unfortunately I only heard it live, but I would assume that in any case it sounded awesome.
Well, because like I think it's the first time I've heard it. Well, certainly a live streamed Wimhurst. I don't know if I've probably watched it in videos, but I haven't picked up on the sound like that. I'm used to it live, and for me it's not the same sound. I don't know if anyone else can jump on, describe the difference. Like it sounded a lot deeper and almost like a Star Wars sound effect kind of thing, rather than like much higher pitched and shorter lasting sound I'm used to hearing in person.
Of course, easy to do it again.
So we can have another live unprepared demonstration again.
Take this away. Let's do it again. If I take these apart, it's going to be better. You mean this one, right? You get the noise just before the crackling.
Yeah, of the crackling. Like it just sounds a lot deeper and fuller than I'm used to experiencing it in real life.
Yeah, and definitely helps if you don't talk over it. So the algorithms don't disrupt the voice, or the sound. But yeah, when you demonstrated it during your presentation, it sounded great. And I asked Diane about her inspiration to do these science experiments, and her answer was Chris. So I wanted to ask Chris, what was his inspiration to start with doing these experiments and go with this path in teaching?
I couldn't hear.
What was your inspiration to start teaching, doing the teaching with all the toys? And stuff?
My high school physics teacher and my father. Yeah, I got hooked at a very early age, and unfortunately or fortunately, I haven't outgrown it yet.
Yeah, so that's great. So it just passes down from teacher to student to teacher to student. And
yes.
A student becomes a teacher, right? Okay, that's great. And similar question to actually all of you, and let me start with Jaffa here, and that is like what would be your advice? I mean, you are both science and artistic guy, right? As you mentioned that you do concerts, and how do you follow like these different passions? How do you find your inspirations in doing all of this?
Wow, actually, I found sometimes I try to find inspiration in fairy tales. Quite recently, about half a year back, I was trying to do the black fire, or the fire that would absorb most of the light and would appear as black. Just because when I was a kid, I read some fairy tale that ended with the story, and she lit the lantern with black light. So these things that seem unreal and then prove possible are a great inspiration.
Thank you for that. And maybe let's continue with Luca. Where did you find all that energy that you just got on us?
I don't know. I think it's many people have been involved into forming me into what I am today. But basically, it's the little things, you know. I got a sister when I was 11, so I spent a lot of time with her at the time, and that was really good for learning how to do the grimaces and everything to talk with kids, which I'm using proudly today, every day. So this was one experience that I would say. And then I first found out my love for not for teaching, but to trying to inspire people when I went to high school for the first time to teach as a part of my studies, and I just discovered that I just enjoy it, you know, and there was good feedback. We were laughing half the time, so I just like doing it, you know. I'm just this is the thing that I really enjoy. So.
Yeah, so we're so grateful to have you here, and yeah, to translate all the energy to you give to our audience. And I believe we have one question from the audience on Anya. Is that correct? Can we have the question on screen?
Yeah, the question is, what is the formula on my t-shirt? So talking about this one, you can find it on a cup. You can also find it on a hoodie that I have there. So this is a formula that is all around CERN, because this is the description, or the short, very, very short description of the standard model, which is basically the description of particle physics, or particles and interactions. And just quickly to go through everything. So the first line here talks about the interactions between particles. The second one here would be particles themselves. Then the third one is how particles get mass. And the fourth one is about the Higgs boson. But if you want to know more about that, you probably need to open the big book on particle physics to get that big, long equation that is, yeah, the actual.
Okay. So the promo follow-up question would be like where we can get the t-shirt like that?
Well, you come to visit me, and then you can get it either at the store, or if you're very kind, from me as well.
Yeah, okay.
Great. I came to visit you, and you didn't give me one.
Well, you got a lot of other stuff.
But you are not kind enough.
Yeah, Michael. You have to work on your kindness. And Anya, while we have you there, also a similar question to you. What was your inspiration on your journey from Slovenia to CERN?
So many people, so many tiny things, just like Luca mentioned. So first it was an inspirational teacher in high school that inspired me to go into physics. Then it was an inspirational professor that inspired me to go into education. And then the biggest influence by far have to be people I met working at Hisza Experimento. So first of all, Luca, of course, and his fantastic performances. Then I was mentored by Chris as well, and just always inspired by what he shows, him and Diane, of course. And in the later years, also Michael, now that I know him, just seeing what experiments he can do with very, very little equipment is just so inspirational to see every single one in this broadcast. Of course, everyone from VIDA also just amazing.
Yeah, it's to you, Jaffa. Feel honored. And okay, so thank you very much for that. And I would like to finish it with a question to Michael. Michael, a common answer to this finishing question was teachers. Teachers were the inspiration. And what would be your advice to teachers that want to be this inspiration, that want to create engaging lectures and so on? Where can they get better, or what can they use to get better with that?
That's a good question, and I guess two parts of the answer. One, don't expect any immediate returns, or don't expect things to work well the first time, or don't expect any extra effort you put in to really get anyone to notice or care initially. But the other part of it is always be open to learning new things from everyone. Like, it's especially from other teachers. That's a recurring theme in my life. Like I've mentioned, I've traveled to a whole bunch of different countries. A lot of the time is to meet teachers and to ask them to share their favorite ideas, their best practices with me, but also always be open to your students and learning from your students. My favorite assignment to give students, I give this in many different forms, is to teach me something and or to come up with something that they teach others. And I'll admit to the students, or like I'll freely say, part of this is so that I get new ideas, so I get better at what I'm doing. So like always be open to new ideas and look for them even in places you'd least expect, like even from students who don't really appear to want to be at school that day, don't really want, like even they have something to offer if you figure out how to bring it out of them, or if you get them on board and you get them like, and I guess I'm rambling on to an extremely long answer for this, but like I want to mention some students I had, like one in particular, I sat through a meeting in France. They have these meetings to like discuss how students are doing. And all the other teachers were saying, this student is no good at my class. All he wants to do is sit and watch YouTube, and he dreams of being a YouTube star. And I said, well, then meet him where he's interested. Get him to make videos for your class. And from my science video contest, like he went from a student who hated science to one who at least tolerated it and was able to teach things to others. And so don't only look for people who you expect to be able to learn a lot from, but really be open to learning from everyone. If you're not learning, you're not living.
Yeah. Thank you very much, Michael. I think it was a great, like actually closing message to our discussion and to the whole stream. As I promised, this was the finishing line. And I want to thank to all our guest performers that made these great live performances possible, and this stream such a great experience for me, and I hope for all our viewers that were great and commented and answered the questions. It made the interactive stream actually interactive, which was great. And with that, I would like to invite the whole Science On team to join me on our physical stage, and with everyone on our online stage. I just want to say goodbye and maybe see you soon, maybe on our next Science On stream, which would be in May, I guess on 17th. I'm not sure. Yeah, 17th. Thank you very much, and have a good rest of the night. Goodbye.
Thank you.
Bye.
Bye-bye.
Bye.
Enjoy. See you.